We have already discussed that glucose can exist in two forms. One is the open structure and the another is the cyclic structure of the glucose. We have studied the open structure of glucose in detail. Let us see the cyclic structure of the glucose. For that purpose, let us study the evidences for the cyclic structure of the glucose. The very first evidence is glucose cannot give the Schiff-Base test, and it can also not give the reaction with sodium bisulfite. To explain this, let us see what the Schiff-Base test as well as reaction with sodium bisulfite is. For that purpose, I am writing the general formula for aldehyde, because we know glucose is the aldehydic functional group. Okay, so if I write the aldehyde like this, a general formula for aldehyde, R can be anything. Whenever any aldehyde react with amines, for amines also I am taking a general formula RNH2. R can be anything. In this reaction, the water molecule is eliminated and we are getting aldimine as the reaction product. Aldimine is commonly called as the Schiff-Base. Therefore, this reaction is known as the Schiff-Base test. Glucose is not giving the Schiff-Base test, that is formation of aldimide, which indicates that the CHO group in glucose is not free. Similarly, let us see the general reaction for sodium bisulfite. For that purpose also, I am taking a general formula for aldehyde RCHO. R can be anything. Wherever we treat this with sodium bisulfite, it gives you bisulfite addition product. Let us see what is the structure of that. This is the structure of sodium bisulfite addition product. Glucose is not giving the formation of bisulfite product, addition product. That means the CHO group in glucose is not free. This is the evidence for the cyclic structure of the glucose. Another evidence for cyclic structure of glucose is the reaction of glucose pentaacetate with hydroxylamine. We have seen the structure of glucose pentaacetate, that is having the free CHO, that is aldehydic group. If aldehydic group is free in the structure, it can react with the hydroxylamine to give the oxime formation. The glucose pentaacetate will not give the oxime formation, and it is the proof for the cyclic structure of the glucose in which CHO, that is aldehydic functional group, is not free. After all these evidences which prove the cyclic structure of the glucose, let us see what are the two different cyclic structures of the glucose. Glucose can exist in two cyclic forms, that are alpha and beta forms. Let us see the structures of alpha as well as beta form in detail. The alpha as well as beta form of the glucose, obviously cyclic glucose, explain all the chemical properties of the glucose. That is the reason it is considered as glucose always exists in the cyclic form. The chemical properties exhibited by glucose are proved by the cyclic alpha as well as beta form of the glucose. You can see the structure of cyclic alpha as well as beta form. Let us have a look. For the alpha form, the position of the OH group on the carbon number 1 is on the right hand side, which I am going to highlight. Whenever the hydroxyl group on the carbon number 1 is on the right hand side, it is called as the alpha form. Let us see the beta form. Again, the carbon number 1, it is having the OH group on the left hand side of the structure, and hence it is called as the beta form of the glucose. Alpha and beta form are also called as cyclic hemiacetal forms. These two forms are having different arrangement of the OH group on the carbon number 1, which is called as anomeric carbon atom. That is the reason alpha and beta form are called as anomers. Glucose can form 6-membered cyclic structure. It is having 6-membered ring in it. That is the reason glucose is called as a pyranose structure. So while naming the glucose alpha as well as beta, we name it like this: alpha, D or L, whatever it is, alpha or beta, glucopyranose, because it is having a 6-membered ring, which is nothing but the pyranose ring. You can see the position of the OH groups in the cyclic pyranose structures, that is Haworth formula of both glucose, alpha and beta. Let us have a look. I am going to highlight again the position of hydroxyl group on the anomeric carbon atom, which is nothing but the carbon number 1. For alpha form, the OH group is downwards, whereas in case of beta form, the OH group on the anomeric carbon atom is upwards. That is the basic difference between the alpha and beta anomeric forms.